In this video, we are going to find out the sensible heat transfer rate of methane air combustion using species transport modeling for a given geometry. So we will do the simulation over here. So already I have done a simulation video for the remaining experiments. So this is a 8th simulation we are going to do. So I will type it as heat flow. So we will do the geometry from first onwards. So this experiment is one of the experiment which is used to find out the total sensible heat transfer rate. So I show the dimension structure. So you can able to see that to find the total sensible heat transfer rate of methane and air combustion using species transport modeling for given geometry. So this is a objective of this experiment. We are going to do this with the help of the Ansys. So this is a dimension you can able to see here. So we will do the dimension by clicking the XY plane. Click on sketch. So make it millimeter. After making it, go to sketch, make it normal, and then zoom it. So we have changed it to millimeter, right? So it is zoomed out. So go to sketch 1 and sketching. So draw a rectangle because it's a structure. In the rectangle, we have the dimensions. The length is 1800 mm. The length is 1800 mm. So it is in mm. So the height is 225, as you can able to see in the presentation what I've been shown. So 225 mm, and then we have to split in the bottom of the left side. It may be at the origin. So click at the point, select the split option and click at the point and make the dimension as 5 mm because it is given in that the methane will be injected. So surface from sketches. So click on sketch 1, then apply, add material, add frozen, then generate. After if you generate, the surface will be created. So this is a structure you can able to see from the presentation. Then update the geometry, then go for meshing and then edit. So from this experiment you can able to learn how to find out the sensible heat transfer. So in this meshing process we have to give the name instructions and then we have to do meshing process. So you can able to see the structure. First we will give the name selection. From left side we will give the air inlet, and then the bottom is splitted. You can able to see in the geometry we have splitted there. So in that bottom you can able to see a small line we need to draw there. So I click on the geometry and then selection name you have to type fuel inlet. So this is splitted in the left hand side, it is splitted into 5 mm and 220 mm. So in the bottom you just type, it may be axis, pipe axis, whatever the reference name you want, you type it. I type it's pipe axis, and the top side I will type as wall, and on the right side it is outlet. So right side I did not split, only left side I have splitted. So right side is outlet, and click on OK. From the name selection you can able to see air inlet, fuel inlet, pipe axis, and wall and outlet. Then meshing, you have to give meshing by divisions. Insert method sizing. In that sizing in the left hand side give 500. 500 is the number of divisions. So it is splitted over here, you can able to see after zooming. So and then you have to do it again. In the bottom we have splitted right, in that you give number of divisions, select, and then you give 10. Number of division is 10. So in this you can able to see it is divided, and then again we need to go to mesh and then method sizing. So click on both the sides, pipe axis as well as the wall. After clicking both the sides you need to give edge number of divisions as 200. So it is mentioned in the presentation, you can able to see, I will show you. So the number of divisions we have splitted as 200. In the outlet we have to give us 510 because in left side we have given 500 plus 10 in the fuel and the air inlet. So in the right side we will give the number of division as 510. So like that the mesh will be happen. Then give, so can you able to see from the left side and right side. So I gave 510, then give enter, then give mesh, generate mesh. So the mesh will be generated. So 5% is generated. So 100% mesh has been done. So you have to give the face meshing, so the mesh has not been uniform. So give mesh insert face meshing, click on the face, apply, you generate mesh. So the mesh will be generated in the face mesh, so you can able to see the uniform meshing. I will zoom it. So you just click update, the mesh has been generated. The mesh translation to the fluent was successful. You can able to see this is a mesh. It's coarse, it's a very fine mesh, so it's looking very black. Then give update to the mesh and then go to edit option. The setup, just give double precision and then click 16 and then start. The fluent will be open. You will be able to see the inlet and outlet arrow marks. So you can able to see the inlet and outlet. So this is axis metric. We need to go for axis metric, and then energy equation we need to on, and then viscous we need to give k epsilon and then click OK, and then go to species transport and then volumetric, and then you give methane air and then edit dissipation and then apply OK. So these are the parameters you need to give from the models, and go to boundary conditions, inlet, air inlet, we need to give the boundary conditions, right? So here the velocity, so as per the PPT what is given, we are typing those things, steps has been given. So these are the machine we have done, and then these things we have done already in the model. And this is air inlet boundary condition to 0.5 meter per second. The air which is coming from the inlet at a velocity of 0.5 meter per second, and then intensity and hydraulic diameter, turbulence intensity 10 and hydraulic diameter as 0.44, you can able to see. So we need to type it 0.44, and then thermal is 300, species as a 0.23 for oxygen. So we have given all these parameters as per the PPT, you can able to see. So oxygen is 0.23, specific method, intensity and hydraulic diameter, and the thermal is 300 Kelvin. So I have given everything, and then apply and then close. So like that we have to give for fuel inlet. You can able to see the three boundary parameters. Here we need to give 80. You can able to see 80 meter per second, and then same 100, 10, 0.01, 80 intensity and hydraulic diameter 10 and 0.01 for the hydraulic diameter. Thermal is 300, and here methane is 1 mole fraction. So these are the parameters we are giving over here, and the outlet we need to give the outlet as well. The outlet, click the same thing, intensity and hydraulic diameter, and turbulent intensity and hydraulic diameter. It is given that 10 and 0.14, 10 and 0.14 and 0.14 for backflow hydraulic diameter. Then thermal species, here oxygen is 0.23, you can able to see the same value, 0.23 as the air inlet what you are given, the same value we are giving over outlet also. Then methods, here it should be coupled, the scheme should be coupled, and then pseudo time step should be global time step, pseudo time method should be global time step, should not be off, and then controls density should be 0.25. This is as per the boundary condition. You need to give all these things, and then initialization, you need to give this hybrid initialization, give initialize, and this fluent has been initialized. The run calculation you just give 200 as number of iterations, then give calculate. So this simulation is one of the important simulation for finding out the total sensible heat transfer between the air inlet which is going over there and the methane with the 1800 mm. It is around 180 centimeter, 1.8 meter, approximately 2 meters. So what is the right is transferring? We are doing it in 2D. So this is a very important thing. So we have given 200 iterations. So it will stop at the 200 iterations. Calculation has been done. So here you can able to see the contours. Here we are mainly focusing on temperature, pressure, and the species mole fraction contours. So click select all. So this is a pressure contour you can able to see. So we will make it as float exponential. So this is a pressure contour as per our boundary conditions what you have given. So if you want a velocity contour, so you can give, sorry, temperature contour, temperature, and then static temperature, click select all and then save. Here it is, give float, apply, and save display. You can able to see the static temperature contour. So here contour is something different when compared to my PPT. So whatever you are getting, that's the result. So if you made any mistake, so we are getting some other contour. So you can able to see here the inlet in the bottom left side. You have splitted right in the time the geometry. So the static temperature you can able to see the contour. So I'm just checking this contour is not same as the PPT. So whatever we are getting, we need to apply all those things. I'm just checking the boundary conditions, those pieces. So everything is okay. So I think we don't need to change anything. Then go to result, flux report. Here you need to give the total sensible heat transfer. This is the result objective what we are giving. Select all and compute. So you can able to see the values: air inlet, fuel inlet, outlet wall, heat of reaction source, as well as the net value. So these are the results what we have got. So the main results are pressure contour, velocity, pressure contour, temperature contour, and the species mass fraction of methane. CH4 is a methane chemical formula. So you can able to see this mass fraction of the methane. So the methane which is flowing in the left bottom side. So you can able to see the contour and save display for the oxygen. So because the air is flowing inside, right? We are giving air as 0.23. So the oxygen presence is very high. You can able to see the boundary conditions. I'm showing for the fuel inlet as well. A velocity of 80 meter per second. So methane is a mole fraction of 1. So these are the contour for mass fraction of oxygen and methane, as well as the temperature contour and then pressure contour. And we have calculated the sensible heat transfer at the bottom you can able to see. So we have done the experiment successfully. So if you want any kind of other thing also, you can able to see the temperature contour as just I'm showing it again. So this is a temperature, a static temperature contour. Under temperature also you can able to see many temperatures. So once if you want to do initialize again, you will initialize it. I have not changed anything. So almost we have done this experiment. I'm just giving 250 iterations. I'm just increasing the number of iterations. So from this iteration, we can able to see how the contour has been changed or not. So to change the contour, we need to give more number of iterations. Is around 1,000, 2,000, 5,000. So that kind of iterations, that number of iterations we need to give over here. So this is a full and full steady state. It's not a transient. So it is calculating. So we have found the total sensible heat transfer values already. I'm just giving for 250 iterations. What is the result? It is changing or not? So you can able to see the contour, the static temperature contour after 250 iterations. The methane is injected over there, right? You select all temperature to temperature. So this is the contour which has been changed after 250 iterations as per my boundary conditions. So you can able to see the contour over here. So this is the experiment we have done. I hope this video is useful for you. For more information, subscribe this channel.